right, so now that we've addressed convective mode as well as propensity for convection to be surface-based, we can talk a little bit more about some of the very important processes that result in the hazards that we experience at the surface associated with these organized convective threats. And we're going to talk specifically about a couple of very specific convective modes and associated threats, starting out with supercell tornadoes. We're talking about supercell tornadoes. There's a very critical process that takes place between the environmental shear's manifestation in the rotating updraft low-level mesocyclone and what's going on near the surface to promote the development of a tornado. Specifically, for tornadogenesis to occur, it's critically important for supercells to be associated with a sufficiently strong rotating updraft accompanied by a hydrodynamic perturbation pressure deficit aloft that accompanies the rotating updraft that amplifies and stretches the surface vorticity that's baroclinically generated along the storm's gust front, specifically in association with the leading edge of the RFD and tilted into the vertical. Now that amplification of stretching the vorticity is done by the dynamic lifting associated with that perturbation pressure deficit that's hydrodynamically driven, that's related to the vertical shear of the horizontal wind and the associated ingestion of that accompanying vorticity into the updraft that's most efficiently done when the vorticity is streamwise. So let's break all of this down. All right, let's say we're dealing with an environment with a lot of streamwise vorticity, for instance. That is one where the vorticity vectors are parallel to the storm's inflow. So with the storm, the air, the inflow, the storm is feeling, when that's aligned with the vorticity vectors, those are the vorticity vectors that are driven by the vertical shear of the horizontal wind. So the vertical shear of the horizontal wind, think about the change of wind speed and direction with height above ground, right-hand rule that's going to cause vorticity about a horizontal axis. When the flow is aligning with vertical shear of the horizontal wind, then the inflow is going to be residing along the vortex vectors, vorticity vectors, vortex tubes, and is going to assume a helical trajectory before even becoming ingested into the updraft. So in the case of streamwise vorticity, we're going to have the inflow already helical since it's along the vortex tubes, and as soon as the updraft forms, it immediately goes into forming a rotating updraft. That initial updraft is already rotating. So let's think about what this rotating updraft is. When we have a rotating updraft, and we'll assume we're looking down over here, a cyclonically rotating updraft, it's going to be associated with a local centrifugal acceleration that's directed away from the axis of rotation. And in order for circular balanced motion to be maintained, that local centrifugal acceleration must be counterbalanced by an inward directed pressure gradient force, or perturbation pressure gradient force. That will only be achieved by removing mass from the axis of rotation, center of mass vicinity, and resulting in a perturbation pressure deficit around the axis of rotation. So when we have the vertical shear of the horizontal wind result in these vortex tubes, and especially when they're aligned with the inflow, that's going to have a tendency of efficiently forming that rotating updraft right off the bat, because the inflow is helical. So that inflow, which goes into supporting that updraft, will be rotating right off the start once we get an updraft. And we get a perturbation pressure deficit. Beneath that perturbation pressure deficit, let's say this is the storm over here, and here is our low-level mesocyclone associated with that perturbation pressure deficit. That perturbation pressure deficit is going to enhance the upward motion, effectively a hydrodynamic perturbation pressure gradient force that's going to associate with enhanced stretching and amplification of the surface vorticity that's being driven by baroclinic generation accompanying the storm's gust front, especially that with the RFD, at the leading edge of the RFD, that's also tilted into the vertical, and it's that vertical vorticity at the surface that's amplified by the low-level mesocyclones induced dynamical lifting processes from the hydrodynamic perturbation pressure gradient force that results in that tornado process. So very sensitive process here. So when we're talking about that cultivation of the low-level mesocyclone, and specifically that rotating updraft, that's most efficiently done, as I said, when we have streamwise vorticity. If we have crosswise vorticity in the environment, that is one where the inflow is perpendicular to the vortex tubes generated by the vertical shear of the horizontal wind, then the inflow is not immediately helical. And when it's not immediately helical, then we're going to have this scenario, again, for crosswise vorticity. Just draw this out real fast. Where our vortex tubes, which I'm going to sketch like this, are going to be not oriented along our inflow. So that's the inflow, E minus C. Here's the vortex tubes. And so our inflow is not going to be originally helical or spiral as it is for the case of streamwise vorticity. And so as a result, when we get our initial updraft form ingesting the inflow like this, which is not helical for the case of crosswise vorticity, we don't initially have a rotating updraft because the inflow is not initially helical. We have to get that updraft to form in the first place, like this, to arch the vortex tubes into the vertical like this, which generates new updrafts because of the dynamic lifting associated with the perturbation pressure gradient force that is going to support dynamic lifting along the flanks of this initial updraft. And it's those new updrafts that are going to be stretching the vorticity that's now oriented in the vertical because of the tilting process to support now rotating updrafts. It's a far more inefficient process to go through. First updraft not rotating, new updrafts, arch the vortex tubes, then get new updrafts in order to support rotating updrafts that are occurring because those new forming updrafts, those new generating updrafts are aligned with the now vertical vorticity. That's a much more inefficient process. So that's why streamwise vorticity is so key, because with streamwise vorticity, the vortex tubes are aligned with the inflow, and we don't have to go through this whole process of arching vortex tubes to get a rotating updraft in the first place. We effectively skip that step, and we get a rotating updraft right off the start. Now, streamwise vorticity, that's actually going to just be a component of the effective layer storm relativity. In other words, when we take the vertical integral of the streamwise vorticity within a layer of air, that's just going to be the storm relative helicity. The vertical integral of this process over here of inflow along the vortex tubes is going to be the actual amount of storm relative helicity. That's why that parameter is so important, because it's describing the potential strength of the low-level mesocyclone that will support the dynamic lifting processes that amplify the near-surface vorticity, or rather the surface vorticity that's baroclinically generated and tilted along the gust front, particularly at the leading edge of the RFD. So the streamwise vorticity is very connected to this perturbation pressure deficit. When we vertically integrate it, specifically when we vertically integrate it within that effective inflow layer, because that effective inflow layer is talking about where all the parcels are in the atmosphere, or the layer of the atmosphere that are subjected to adequate amount of buoyancy and lacking inhibition to serve as the updraft material, or the inflow corresponding to that convective updraft. That's going to get directly at where, or specifically what's relevant for cultivating that perturbation pressure deficit in the column. Because if all of our lowest level parcels are associated with a tremendous amount of convective inhibition, they're not going to be susceptible to forming that low level mesocyclone. It's going to be the layer of air where we have enough buoyancy and lacking inhibition to support that generation of that perturbation pressure deficit that's measured by the effective layer storm relative helicity. This is a concept and parameter that, again, Storm Prediction Center lead forecaster Rich Thompson created. This is used widespread across the National Weather Service and across the operational meteorology community for understanding the potential for that perturbation pressure deficit to potentially amplify or stretch that surface vorticity that's generated along the storm gust front, leading edge of the RFD, for instance, and tilted into the vertical. And so that's why effective storm relativity is such an important concept to be considering, as it's going to be measuring the amount of streamwise vorticity available to that developing convection. And that's going to be very critical for considering in tornado threat assessment. So we've covered in terms of supercell tornado threat. Also want to talk a little bit about squall lines. So we're talking about, first of all, supercells. All hazards are on the table. Tornadoes, damaging winds, hail. As far as squall lines are concerned, certainly damaging winds and possibly tornadoes are going to be the main threats to be considering in terms of severe weather threat, where we see the progressive forward propagating components, surges within the convective lines, QLCSs. Those are going to have a tendency of being areas where the damaging wind potential is going to be relatively greater. Tornado threat is going to be focused in terms of being maximized around areas where we have line breaks, inflections in the line. We're going to want to make mention of the 3 ingredients method for tornado threat assessment accompanying QLCSs, specifically the mesovortex threat assessment, which is going to have some linkage to the tornado threat. So we're talking about 3 ingredients. We're talking about the mesovortex threat, mesovortex potential. That potential is going to be maximized in portions of the squall line where we have a balance between the cold pool and the low-level shear. So that cold pool low-level shear balance or slightly low-level shear dominant. Those are going to be portions of the line to look out for enhanced mesovortex potential, along with adequately strong line normal 0 to 3 kilometer shear, and also looking at surges, rear inflow jets as being important foci for potentially enhancing tornado threat within the QLCS. But it's also very important to consider the deep shear vector being oriented orthogonal to the QLCS as well for assessing tornado potential with the QLCS, as that deep shear vector being oriented orthogonal to the convective line and gust front is going to have a tendency of supporting regenerative convective cells, maintaining residence time along that gust front or keeping up with the gust front for those free generating convective cells that will help amplify, stretch the gust front related baroclinically generated vorticity along that gust front that's tilted into vertical, as those free generating convective cells are able to keep up with that gust front when the deep shear is oriented perpendicular to the gust front and that line. Also of note, when the deep shear is oriented orthogonal to the convective line, in addition to amplifying the surface vorticity with the presence of free generating convective cells, that will also have a tendency of propping up the overall convective system as well. And this will also have a tendency, when the deep shear is oriented orthogonal to the convective line, those free generating convective cells keeping up with that gust front will have a tendency of also refreshing that gust front and associated baroclinic production of vorticity that can be tilted into vertical and then amplified for the production of QLCS tornadoes. And so those are all considerations that we have to take into account when performing convective threat assessment. With those modes, there are going to be many other convective modes and variations of them that are going to be important for assessing the overall severe weather threat. Convection allowing model guidance plays a critical role in terms of getting a perspective on how model simulations that can resolve finer scale details of atmospheric motion and other quantities are evolving, and the convection allowing model guidance, not only looking at reflectivity and composite reflectivity, but also looking at many other storm scale attributes such as updraft helicities, 10-meter winds, max winds, also looking at things in an aggregate sense, multiple convection allowing models, convection allowing ensembles, the high resolution ensemble forecast system. Look at convection allowing models in an aggregate sense in order to put all the pieces together to get some idea in terms of what the CAM guidance is suggesting in terms of convective behavior and morphology. Looking at neighborhood probabilities, how the clustering of various convective attribute fields is lining up from these model solutions. Now, CAMs are not perfect, and that's why the human is so important in order to be able to assess all of these details, to find the areas where the HER or various other CAMs or CAM ensembles are off. Zones of recovery are going to be critical for conditional severe weather threat assessment, and are going to be very much struggle to be depicted correctly by models owing to interdependencies on convective processes for which predictability can be low, particularly in weak forcing for ascent patterns. And so as a result, there is a tremendous need for the human to maintain a very discerning eye on all of these various factors in terms of performing convective threat assessment. When we're talking about the probabilities corresponding to severe thunderstorm, hail, wind, and for tornadoes, we're talking about the probability of event occurrence within 25 miles of a point. And when we're talking about the hatched areas indicating significant severe weather potential, we're talking about at least 10% probabilities of significantly severe wind, or 65 knot, 75 mile an hour or stronger wind gusts occurring, significantly severe hail corresponding to 2-inch or larger diameter hailstones, and for significant tornadoes, EF2 or stronger tornadoes. That's what we are talking about, the 10% probabilities of those occurring, again, within 25 miles of a point. That's what constitutes the hatching area. So there are very specific probabilistic quantitative measures that go into the foundation of the actual categorical outlook. And again, remember, the convective mode and the base of the effective infill layer are absolutely critical to be assessing, in addition to all the magnitudes of the ingredients that are all favorably overlapping in time and space when drawing these probabilities and coming up with some threat assessment. If we're expecting there to be a lot of sustained supercell structures amidst a wide open warm sector with a broad area of surface-based effective infill layer air, broad warm advection pattern therein, with large amounts of SRH accompanying a veering wind profile, it's going to certainly be upping the tornado potential. Higher end tornado probabilities could be warranted in those particular cases. We'd be seeing that area of pressure falls associated with the warm advection pattern. So there's a lot of different clues in the observational data sets we could be considering in terms of making this assessment. The overall scope of the warm sector air and surface-based effective infill layer air will be truncated by antecedent outflow. That will challenge things considerably because it's not the best, or it's not always displayed the best in terms of model guidance. It's tough to really get down to the level of cold pool, preceding cold pool deposition and subsequent evolution. And to capture that perfectly correctly by any model, you can't really demand that much from the models. That's why there's such a critical need for the discerning eye of the mesoanalyst for how these various parameter spaces are behaving in support of severe weather threat. You know, certainly if we have confidence in an intense forward propagating convective system to advance through a region of ample surface-based buoyancy, supporting a dense concentration of severe wind gusts, that would be corresponding to enhanced, moderate, even high risk if we're expecting significantly severe winds embedded with a dense concentration of winds. But a lot of those convective structures can sometimes evolve in more weakly forcing for ascent scenarios, which is going to limit the overall predictability and therefore total probability of threat. And so being able to discern conditional threat versus unconditional threat, predictability, levels of predictability, storm coverage, convective mode, all go in to the outlook assessment, which you'll be seeing here in this final video clip. In general, the various outlook categories correspond to both coverage as well as intensity. If we're expecting isolated severe storms, generally talking about marginal, isolated to widely scattered, talking about slight risk. As we go towards enhanced risk, we're talking more of a scattered severe weather coverage. For moderate risk, we're talking more numerous and intense severe convection. When we get to high risk, moderate and high risks, we're really talking about a lot more confidence in higher end, greater coverage, severe weather episodes. We're talking about, for high risks, the most intense, the most memorable severe weather threats with high coverage and numerous intense severe weather episodes within the high risk area. That would likely result in a memorable severe weather experience for many, with high confidence in that occurring. You could see more details about each of these outlook categories on the Storm Prediction Center website. Remember, all those categories translate over from the probabilistic severe weather, individual severe weather hazards, and that's all going into the overall threat assessment. There's going to be some nuances and gray zone in terms of where we draw the lines, and so that's where there's a very critical need for that human threat assessment in order to allow for some degree of consistency and, very importantly, communication of the threats as we prepare this outlook information. So we're going to conclude with just a very quick discussion on some final considerations as we put all the pieces together. So when we're talking about convective outlooks, there are a lot of things we got to consider. And I would just say always think about taking a step back from what you're doing, what you're completely engrossed in, and just ask yourself, does this make sense? Does a pattern like this support the type of severe weather threats that I'm forecasting. You got to always just kind of take a step back and clean your mind and try to think, does this make sense? Is this consistent with the types of convective modes that I've expected? Is this consistent with my notion of effective inflow layers being based at a particular level at the surface, elevated, etc., etc.? Is my forecast of severe hail, wind, and tornadoes, is that consistent with the considerations of various magnitudes of the severe storm ingredients that are favorably overlapping? So we always have to just kind of step back. Is this making sense? Reality checks. And a very important part of reality checks is asking our coworkers, can our speculations, can our assessments stand up to the test that others may place in front of us? Are there questions that they have that could potentially improve the outlook? The outlooks, it's a very much collaborative product. With the internal collaboration at the Storm Prediction Center, we're talking about decades, combined centuries of experience, all collected together, where people work together with one another in order to improve and enhance these outlooks, or rather make them better. And certainly there's an element of collaboration within the broader National Weather Service structure, but that internal collaboration is absolutely critical in terms of getting experienced advice from coworkers and getting those reality checks of, does this outlook and does the threat assessment that you're putting forward make sense? Many other nuances involved in that in terms of people skills. You know, if you have a very abrasive personality and you make it very challenging for other people to ask questions, that can kind of stifle the opportunity to get that advice or feedback in terms of how someone thinks the outlook is actually, what kind of shape it's in. And so being very open and cultivating a warm, inclusive atmosphere where people feel comfortable providing feedback, receiving feedback is absolutely critical. And so, you know, if you're a very passionate, kind of like me at times, very intense personality, you know, we got to police ourselves sometimes and kind of take a few steps back and chill out a little bit so that we're more receptive and people are more receptive to providing us feedback, and so that we're not constantly in a state of intensity. Being able to police ourselves and be a lot more able to be approachable is absolutely critical to cultivating that atmosphere of one where people are all contributing to a very important collaborative product that's highly visible and really the springboard for a tremendous number of operational forecasting related decision making that occurs within the weather enterprise and tangential and partner communities. More on the science side of things, you know, we're addressing conditional type threats. If we're thinking about some potential for a watch or a high conditional severe weather threat and a non-zero, but low potential for actual storm formation, like a dry line scenario, you know, in some circumstances that one may want to defer more towards slight risk if there's a possibility of watch issuance, since there's going to be some connection between watch issuance and slight or above convective outlook categories. And so identifying conditional risk and being able to message that appropriately is certainly a challenge, and sometimes deferring for some of the very conditional but high conditional severe weather threat environments, especially conditional significant severe weather threat environments where there's at least some convective potential, those are certainly going to warrant different approaches to the actual communication of outlook information. Also, the importance of considering that it's harder to downgrade an outlook than it is to upgrade an outlook. Sometimes if there's uncertainty in a certain scenario, leave it as it is, go with the status quo. If there's uncertainty, there could always be time later in a subsequent outlook to perform an upgrade is absolutely important to consider, especially if predictability in certain scenarios is limited, and that could be addressed in later outlooks if there's uncertainty. Sometimes the status quo is the important consideration, but if there's enough confidence to perform the upgrade, certainly that would be very appropriate if conditions warrant. But again, it can be harder to downgrade than it is to upgrade. We're going to conclude this with a quick discussion of General Thunderstorm. This is what we'll be wrapping up the Convective Outlook with. Remember, General Thunderstorm areas indicate at least 10% probabilities of thunderstorms occurring within the General Thunderstorm areas. We're performing the General Thunderstorm threat assessment. We are looking at areas in which we have a sufficient buoyancy present, MU cape of at least 100 joules per kilogram, although we can have less than that, particularly in some of the more stronger forcing for ascent scenarios. Also, we need to have our buoyancy extend deep enough into icing layers aloft to promote the charge separation capable of intensifying electric fields strong enough to support lightning development. That's going to be associated with equilibrium level temperatures that are colder than -20 Celsius, certainly enough lift to be present to get storms to form in the first place. Considering the notion of using the cloud physics thunder parameter is important because a lot of what we're talking about with buoyancy extending deep enough into the icing layers aloft to promote the charge separation, electric field intensification, lightning development is very much related to cloud physics phenomena. And again, this is an important consideration for defining the overall extent of lightning-producing threat areas in the convective outlook.